Now I want to talk about a few companies that are doing things. Defcalion Research, originally out of Greece. But they had worked with Rossi on, and so they had worked with this nickel and this hydrogen, which is different than the original palladium that most of the researchers done in the early years. And they use nickel and hydrogen again, but it must be replenished about every 6 months. So you don't have to refuel this very often. And they're working on a 5 kilowatt reactor. There it is. There's your 5 kilowatt fusion reactor. You don't see any lead shielding around this. You don't see any danger radiation warning signs around this. You don't see any concrete pit underneath there in case it melts down kind of a stuff. Pretty benign equipment. And so, you know, they published pictures of what they're doing. It's pretty open. You can see it, how it works. And they got theories about what's happening. And it's all about getting that nuclear active environment in there. Finding that thing that Fleischmann and Pons spent so much time trying to figure out what is it that causes this fusion reaction to happen. And so they published an actual spec of their equipment, of what they're trying to build. I got it here someplace in a pile. Here is what their reactor is. It gives a detailed spec. There's about 20 pages in here about every piece they use in that reactor. The only thing they don't tell you is that catalyst that they used to coat the nickel powder. And so that's what they hold. So they expect commercialization of this third quarter of this year. You can go to that website and you can find that information. Brillion is another company that is started by a longtime researcher, Robert Godes, in Berkeley, California. And they use metal hydrides, and here's the actual description of what's going on, and I don't understand it. But they have a reaction that is very controllable. They can start it and stop it at will. And they use electromagnetic pulses, and they start this reaction of creating hydrogen, again, inside a metal lattice structure, fusing together to create helium. And it goes through several stages. Hydrogen, protium fuses into deuterium, into tritium, and then into helium-4, or to hydrogen-4, which goes right into, decays into helium, and you get all of this excess heat. Here's their equipment. Inside that reactor on top of that table is where it's happening. So they've got a, they also have got quite a little bit of money. They've raised $2 million in 2012, and they're now going after a $20 million second stage of financing. So again, serious money being put into this. They've signed a license with Sunrise Securities in New York, and the condition being that they have to go out and retrofit an old coal-fired power plant. Take the coal-fired boiler out and put a fusion boiler in. And that's the deal. And that's what they're working on. And there's just a pictorial of what their hot tube boiler, they don't call it cold fusion, they call it hot tube boiler is. So they're going to be issuing licenses, additional license by the end of 2014, hopefully have this thing up and running as a demo by then. Lenr, and I met this gentleman at the conference, Dr. George Miley, 5 colleagues from the University of Illinois. They have achieved 200 watts of excess heat, not using nickel, but using zirconium oxide, but again, with hydrogen or deuterium. And they get their product right from the Ames lab, right in Ames, Iowa. They get their product. And they have generated about 7 kilowatts. And here's what they're trying to build. This little thing, it's about twice as big as my wine bottle now, 3 times as big as a wine bottle. Got one moving part in it, and it's a fan. It's a fan down the left side to cool off the coupled thermoelectric generators. No moving parts. You put hydrogen in, you get heat out, and you get heat caused by fusion. So they're saying that this is going to cost about $3,000. I don't believe them. It'll cost $6,000. And you got to refuel it every 6 months for $500. And if you take the kilowatt hours divided by 500, you get 7 cents per kilowatt hour for the fuel. They have, he's one of the few people that have U.S. patents. This is on Lenr, which has been very hard to get. So they're expecting the prototypes this year. Lattice Energy, LLC. This guy, Louis Larson, he's not a researcher so much as he's just an enthusiast, and he wants to get, accelerate this whole thing. And this guy comes up with the most colorful PowerPoint slides there are on the internet. And that's why I like this guy. And he demonstrates, okay, here's all these energy sources, here's the energy density, and you look down at the bottom, and LENR is on the bottom of this table, and it's 57 million is the energy density, watt hours per kilogram of reactant versus all these other things that, it blows the world away when it comes to energy density and being able to do things. And he's saying that someday, hey, it's not very far off, it's in my dreams, it's going to be this. I'm going to have something like this, and this is going to be my little LENR type of a reactor. So I don't know if he'll get there or not. Blacklight power, a little bit different approach. And it's a solid fuel catalyst. And it converts H2O, hydrogen, some sort of a hydrogen, but it's in the form of a solid fuel. And it's the strangest thing I've ever seen. He's got these gears, and he puts a lot of electricity through this reactant at the right time, and it creates a plasma. So it's a hot fusion reactor in a sense, but it's on a little tiny micro scale. And then he runs this hot plasma through a magnetohydrodynamic generator, a converter. And if you've been in the power world, you know what that is, but it's a way to create electricity out of a hot plasma flow gas. And it produces 10 times as much power as you put into it. And so there's a picture of it. It's a little mock-up. It doesn't look nearly that neat with the prototype you have, and you can go on the internet right now and see a demonstration of it. It's hard to understand what's going on until you read it all and you say, hey, that's kind of neat. So again, about the size of this table. Going to produce, 100 kilowatts. And what's the fuel? It fuels hydrogen. So very neat. Other companies. Dr. Piantelli from Italy is working on a 10 to 100 watt item today. Energetics, LENR cars. This guy just wants to figure out some way to use this to power cars. I guess he doesn't like to buy gasoline. And it's hard to understand how this guy is going to make it happen. But you know what? It takes people like this in the world to make things happen, people that are excited about it. Hunt Utilities Group. This is up in Minnesota. They're working with the Martin Fleischmann Memorial Project. And they are trying to build this equipment that can be sent anywhere around the world to demonstrate LENR. Quantum Potential Corporation. And this is where they've produced fusion in cavitation. And there's been now 6 demonstrations of cavitation. You know what cavitation is like in a pump where you get little bubbles inside in the liquid or water, and these bubbles collapse. And it's usually bad. Cavitation is bad in the pump world. But cavitation is a small bubble that collapses in on itself, and if you create it just the right way, you can get a tremendous pressure on the molecules inside there, and you can actually have fusion. So fusion has been observed, 7 different experiments. Here is a simple pump. It's not a simple pump, and it used deuterium water, which is kind of expensive. And they said, hey, this thing will give us 100 kilowatts of heat. Again, the fuel is hydrogen. So there's a lot of work going on around the world. Jet energy. This is another MIT professor. I met this guy. Brilliant guy. He's a medical doctor who worked in radioisotopes and therapy. And he got interested in LENR. And he developed a little device, a fuser, an electrochemical cell. And he said, well, this is neat. And then so he went on to develop another device called he kind of liked the word fuser, so he called it a nanner. And a nanner is about this big a thing. This is like a 1/4 watt resistor. 2 leads on it. You put electricity through it. And normally in a resistor, you put electricity through it, you generate a little bit of heat in the resistor. Except with the nanner, you get more than the I²R loss, which is normal. You get like many times the I²R loss. So you put a little electricity through this, and you get a whole bunch of heat out. And you say, well, that's neat. What good is it? What can I do with this thing? And so the point is that he's achieved a ratio of 20 to 1. So how would that be useful? Well, lithium-ion batteries, we got a lot of them. When they get really cold, and Gary knows this, they don't perform as well, do they? Now, what if you could take just a little bit of that electricity from that battery and warm the battery up with it? You would get a lot more electricity out of your battery, wouldn't you? So there's the first application of his little product right there. So, and here's some tests, and it's just amazing to see this, and here's the experimental results, and voila, you get this extra heat out of it. And so, even though it's, you only get a watt out, the energy density for the energy that's used inside there's a little bit of hydrogen in that thing, is 10 million times that of gasoline. He's now working on the M manner. Now, MIT must have felt guilty about really destroying the reputation of those guys. So now you can go to MIT and take a Cold Fusion 101 course, and it's online. You can take it online. They've got one coming up in March 21. I was thinking about going out there and actually taking it in Cambridge. And Peter Higgelstein there, one of the other brilliant guys that I met him, and just in awe of his intelligence. He is the guy that came up with the 200 theories of, is down to one. So he's also teaching it. And then here's a regular old guy, Bob Higgins. He formed a little cutie. He is a guy I met at the conference. He's a Motorola research engineer. Worked for the company for his entire career. He retired after 37 years, worked in a lab, and he got interested in the last few years. He was an electrical engineer. He says, this is really neat stuff. I wonder if I can do this. And so he got some lab equipment on the cheap, put it in his garage, built his own little reactor, and this guy worked in a research lab for all of his career. He knew how to do things. And so after trying this out, he achieved thermal outburst that lasted 40 to 100 seconds. So here's a regular guy, could be me, except I'm not as smart as Bob. But it's a guy that starts from scratch 2 years ago and says, hey, I want to achieve this. So he published his work, a little white paper. I got copies of it up here if you want it. And in that white paper, he says, the thermal events observed during preliminary testing of this powder in H2O are consistent with the previously reported LENR mini explosions. And so he said, at present, there is no other supporting data to report these events having a nuclear origin. So in other words, he says, hey, what I observed can't be explained by anything else. So here's Bob in his garage. There's his lab. Here's his, I got this from Bob right here, this nickel powder. This is what it looks like under a scanning electron microscope. These little chunks of nickel, and then he coats them with this catalyst that's top secret. Well, he figured out what it was. Iron oxide, Fe3O2. He said, that's got to be it. That's got to be what Rossi used. So he coated it in there, and then he baked it in a furnace. These research guys, it's quite a little process. Comes out of the furnace at that top thing right there, and he takes his mortar and pedestal, or however you say that, grinds it up, takes some more electron microscope pictures of it, and this is what it looks like after it's gone through the furnace. This is the stuff. This is the stuff where you get a cold fusion out of. And if you blow up on there, do you see those little whiskers down there? That's little particles of nickel coming out, growing out of those crystals. So here's his test setup here. Schematic drawing of it. He's got a bottle of hydrogen. He's got a test reactor down the bottom. He's got those 2 buckets of water to cool things off. There's all of his lab equipment and his little reactors off to the right there. And there's the data. See those 2 little purple things? Unexplained humps in the data. That's my excess energy. First time out, he achieved excess energy. So let me step back just a little bit. Hot fusion. That's where the billions and billions and billions of dollars are going into hot fusion. In the United States, there's the National Ignition Facility in Lawrence Livermore National Laboratory in California. In 2013, they announced, if you recall, hey, we finally got out more power than we put in. And And there's a picture, a pictorial diagram of this facility. You know, this is really big. That's really expensive equipment in there. Lasers and supercooled conductors and superconductivity, and that's a different picture of a reactor, but pretty pricey stuff to make that happen. And then right now we're building the International Thermonuclear Experimental Reactor, the ITER in France. We're one of 7 countries, $18 billion. Here's just part of the footprint. You see all those the re-rod in there? Look how thick that is, and look how big that is. And guess what? This is the cheap stuff here. This is the cheap stuff. So lots of money in it. 2013, Lockheed Martin said, hey, we think we can develop a 100 megawatt nuclear power plant by the year 2017, get it ready to go by 2022. So out about 10 years, hey, well, I think we can do it. We can do it. Give us enough money. And the neatest thing is, last week, Jamie Edwards became the youngest person ever to achieve fusion. Did you know that you can go home and achieve fusion yourself? It's not very important if you do it. And it's called a device called the Farnsworth fuser. There it is. There's a picture of it. That's not Jamie, but there's a picture of it. And it's, you know, use electricity and you create a little bit of fusion in there. You know, it's not a big deal. $2,000 and he did it. But again, what's the big deal about that? How can you use that to help solve the world's problems? You can't. So, comparing hot fusion to cold fusion. One of the books, a good book, is by Edmund Storms. And the foreword is one of the better parts of it, and it just talks about, hey, cold fusion. It appears to be so simple that any household could afford a device and hope to use it to supply all of their energy. I mean, if it's this big, and it's no elaborate type of equipment, surely we can use this for our own around the homes. Instead of the huge central generator of an unimaginable complexity and cost, the Fleischmann-Pons device is something that a bright high school student might understand and afford to construct. So you just compare that picture I had of the INF in Livermore, California, versus something you can hold in your hand and say they both are producing excess heat. So anyway, he goes on and makes some very, just really pertinent observation and says, in short, brute force is used to cause hot fusion, while cold fusion requires a complex environment, in which a process similar to seduction is used to make it work. That's what Fleischmann and Pons were doing. They were trying to seduce those hydrogen to get it in just the right spot, and then magic occurs, And cold fusion has been difficult to replicate, very difficult until the last few years. Hot fusion has been difficult to make useful. Hot fusion is very dangerous, lots of neutrons and all that.